Okay, Chemistry 111, this is practice exam 5. This is the second part, and we're on question number 36. It says, indicate the type of hybrid orbitals used by the central atom in carbon tetrachloride. So if we look at the Lewis structure of carbon tetrachloride, we can see that the carbon is bound to the 4 chlorines. And so another way of saying that is that the carbon is or has 4 regions of electron density, and therefore it is going to be sp3 hybridized. And so the answer is E. The carbon is sp3 hybridized. Question 37, which of the following species have the same geometries? Well, if we look at A is amide, as I told you earlier on, and we looked at the Lewis structure in the molecular geometry of this earlier this evening, so I'm not going to spend a lot of time on that. The amide looks like this. It is bent, and then beryllium hydride, BeH2, is going to be linear because beryllium is only going to have 2 bonds. If I go over to B, I see that my amide NH2, which we already looked at, NH2 minus, is bent, right? And then if I look at water, it is also bent. But then if I look at BeH2, it's linear, so the answer can't be B. If I move on to C, water is bent, and beryllium hydride, H2, is linear. And then if I go to D, I see that NH2 minus, the amide ion, is bent, and water is also bent. And so the answer is going to be D. NH2 minus and H2O are both bent. Number 38, which of the following substances display an incomplete octet in this Lewis structure? Didn't we already do this question or something almost identical to it when I was thinking about exceeding an octet? The answer is NO. It's a Lewis structure that looks like this, where the nitrogen doesn't have a complete octet. Right, it's surrounded by 1, 2, 3, 4, 5, 6, 7 electrons. We call that a radical when we have an unpaired electron. Number 39, the geometry. And when it says just geometry like that, it means the same thing as saying molecular geometry of the sulfur tetrafluoride molecule is, well, if we tally up the total number of valence electrons in SF4, sulfur tetrafluoride, we have 6 from the sulfur, plus 7 times 4, that's 28 plus 6, that gives us a total of 34 valence electrons. If I draw a Lewis structure of SF4, if I put 1, 2, 3, so let's draw a Lewis structure first. I'll just surround the sulfur with the 4 fluorines like that. Well, I've used up a total of 8 times 4. That gives me 32 valence electrons, so that means I've got 2 left over. I'm going to put them on the central atom like that. So now I've got a sulfur surrounded by 4 bonds and 1 lone pair. That's going to mean that my electron geometry is going to be trigonal bipyramidal, right? Because I'm surrounded by 1, 2, 3, 4, 5 regions of electron density. Now, again, that's my electron geometry. Well, what is my molecular geometry? Well, let's draw what it would look like, because we remove one of the atoms from the equatorial position and replace it with a lone pair. So our molecular geometry will not be trigonal bipyramidal. Rather, it will be seesaw, which is also called the distorted tetrahedron. So this is seesaw. I find it easier to remember seesaw. Number 40, classify the oxygen-hydrogen bond in methanol, CH3OH, that's methanol, it's called wood alcohol. Is that ionic, polar covalent, or non-polar covalent? Well, there's a pretty big difference in electronegativity, isn't there? Oxygen has an electronegativity of 3.5 and hydrogen is around 2.1. That means the delta En is the absolute value of the difference between those two, 3.5 minus 2.1, which equals 1.4. Now, ionic, this is usually when we have a difference in electronegativity that's greater than 2. Polar covalent is going to be somewhere in the neighborhood of around, 0.5 to 2, 2-ish, right? There's no hard and fast numbers here. But non-polar covalent is going to be something that's, less than 0.4 or less than 0.5, something like that. So we'll put less than 0.5 approximately. And you can see that 1.4 falls well in the range of polar covalent. So this is a polar covalent bond. All right, the last 2 questions deal with molecular orbital diagrams. The first one is, what is the bond order in F2 with a negative charge? And remember, I'm going to give you the valence molecular orbital diagram for Li2 to N2 and then O2 to Ne2, right? So if I'm not going to project that right now, but remember, you get the MO diagram for Li2 to N2, and then we get a different one for O2 to Ne2. Well, luckily, fluorine's going to in here between the oxygen and the neon, so we're going to use this molecular orbital diagram right here. And I'm going to draw that out. But before we do that, let's calculate the total number of valence electrons in F2 minus. Fluorine has a total of 7 valence electrons. So if I have F2, that's going to be 7 times 2, and then I'm going to add 1 for the negative charge. And that gives me a total of 15 valence electrons. Now let's draw out our molecular orbital diagram. I'm going to reproduce the same one that's in the book. So I'll write it out here. So I've got a sigma 2s, sigma star 2s. Did I put stars where I didn't mean to put stars? I did. Fix that up. There we go. So now my antibonding 2py, pi star 2pz, and then I have my sigma star. There we go. All right. I'm going to select this because I'm going to need it for the next problem too. Copy like that. Okay, so let's fill this up with our 15 electrons. We're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, like that. Bond order is equal to 1/2 the number of bonding electrons, okay, minus antibonding electrons. So that's going to be equal to 1/2 times. Where are the bonding electrons? Anything that's not in a sigma or a star. So 1, 2, 3, 4, 5, 6, 7, 8. So I've got 8. Where are the antibonding? The antibonding or anything with a star. 1, 2, 3, 4, 5, 6, 7. 8 minus 7 is 1 times 1/2. Our bond order is equal to 0.5 or 1/2. Question 42, consider the species O2 plus, oxygen, and O2 minus. Which species will be paramagnetic? Remember, in order for something to be paramagnetic, it's got to have unpaired electrons. If I look at these species, O2 plus, O2, and O2 minus, the number of valence electrons for each one of these. Okay, O2, we'll start with that one. It's the easiest one. Oxygen has 6 valence electrons. 6 times 2 gives me 12. O2 with a negative charge is going to have an extra electron, 13, and O2 with a positive charge is going to have 1 less electron. Now I've just put up the valence molecular orbitals here. So we'll start with, why don't we start with O2? We'll start with these 12 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This has unpaired electrons, and so it is going to be paramagnetic. Let's try O2 plus 1. All I would have to do is remove one of those electrons. You can see that I still have, oops, I didn't mean to do that. You can see that I still have an unpaired electron. And so that means that O2 plus is also paramagnetic. And if I want to do O2 with 2 minus charge, I'm going to add 2 electrons from what I've got now. So I'd put 1, 2 like that. And you can see that I've still got an unpaired electron. So this would also be paramagnetic. And so all 3 of these species are in fact paramagnetic. That concludes the practice exam.